Welcome to GetX AIML. In this video, we'll try to understand the concept of orthogonal vectors, orthogonal subspaces, and orthogonal matrices. Why they are required? These have certain properties. Okay, these properties, when applied on our solutions or our problems, then we can transform into some other form for the easy solutions. You can understand it like that. So orthogonal means what? Orthogonal means, we just remember there are two vectors, v1, v2. They are perpendicular to each other in this space. Okay, they are perpendicular to each other in this space. For example, like this. Okay. That is a concept. Perpendicular means the angle between them is 90 degree. Now we'll understand how this helps. Okay, so let's begin. Okay, vector length. Already you have studied this concept. What is the vector and vector length? Now, to take, we already know if let x be a vector. Okay, like x1, x2, xn. Okay. Now, how did you find the length of this vector? Length of this vector is square root of all this. X1 square plus x2 square and so on plus x square. Now, if you see this as in two ways, multiplying this vector with x transform. Say x into x transform. Okay, so this is nothing but, you can write it as x1 into x1, okay, plus x2 into x2 plus so on to xn into n. Okay. So I'll get the same result, x1 x2 plus x square 2 square plus up to so on. This is as good as writing x transform x into x transform into x. Okay, so that means what? We'll try to understand. Okay, what is the orthogonal vector? Two vectors x comma y belongs to Rn are orthogonal if x transform into y equal to 0. So there is a vector x and then there is a vector y. So this is a x1, x2 up to xn. There is vector y, say y1, y2 to yn. Now if I take x transform and then multiply with vector y, I should get the resultant as 0. The dot product of these two vectors should be equal to 0. Then we say that x and y are orthogonal. It means what? In this space, say this is my x transform, sorry, this is y, and say this is my x transform of x vector. Then they are perpendicular to each other. When they are perpendicular to each other, the dot product, okay, is equal to always 0. That is the property. Now, what is the orthonormal vector? Okay, the orthonormal vector is same. Two vectors are orthonormal if they are orthogonal, and one more condition you have to have. The length of each vector should be 1. That is, here if I take in this example x transform into y, that is nothing but x1 into y1 plus not square root dot product x2 y2 so on up to xn yn be equal to 0. Then it is orthogonal. What is orthonormal? Orthonormal is with this condition has to be satisfied, plus the length x should be equal to 1, the length of this, and both vectors y should be equal to 1. Then we call it as orthonormal. So orthonormal is a special case of orthogonal where the length of the vector should be equal to 1. Okay, how will you check? So given these two vectors x and y, check they are orthogonal. So you take x transform of x is transpose of x is 2, 2, minus 1. Then my y is equal to minus 1, 2, 2. So I'm writing it in this form only, okay, in column form, so that it is easy to multiply. So x transform into y is equal to multiply this. So 2 into minus 1 plus 2 into 2 plus minus 1 into 2. So this will be equal to 0. So hence x and y are orthogonal. Next, what is orthogonal set? Now we have defined it for only one vector. Let us consider now set of vectors. A set of non-zero vectors. Okay. So v1 is a non-zero vector. Up to vk, there are k vectors that are mutually orthogonal is automatically linearly independent. So see, when you solve a system of linear equation, you checked the linear independence. There you multiplied c1 v1 plus c2 v2 plus c3 v3 so on up to c1 v1 equal to 0, and then you said if the trivial solution is this equal to cn equal to 0, then all the vectors are linearly independent, right? So using orthogonality also we can find them. So when you can find if they are mutually orthogonal. So if all these vectors are mutually orthogonal, then definitely this will be 0, because sum of this, right? That's what we're doing. v1, v2, if you take any pair, that dot product will be 0. Hence, they are orthogonal. What exactly it means conceptually? Say, let me take only three vectors v1, v2, v3. So linearly independent means what? And they are orthogonal. So if you can visualize, so these are my three vectors v1, v2, v3. They are orthogonal, means the angle found between any two vectors is 90 degree. This is the meaning. So why they are linearly independent? See, there is no overlapping between them. Let us say there is a xy plane. So there is a xy plane, and I have two vectors v1 and say v2. Now if you observe here, this is say 0 and y is some value, say 3. This is x is 0, y is some value, say 2. So these two are the vectors. Now this is 4 and 2. Now if you observe, so they are parallel to each other. Okay, they are parallel to each other means they are not orthogonal. Why they may be linearly dependent? Because I can write this vector v2 or v1 is equal to 2v2, right? So that is, there is a linear dependency. v2 is dependent on v1. If I scale this by 2 times, I will get this. So this is nothing but I can write this as v1 is equal to 2v2. So there is a linear dependency. So orthogonal means there is no, they are to the right angle to each other. So there is no dependency. Okay, so here I can write v equal to some constant into v2. Then they become dependent. That is a concept here. Next. So given this an example here. So v1 equal to this, v2 equal to this, and v3 equal to this are mutually orthogonal. So how will you check? Between any two pairs, the dot product should be 0. Is v1, v2. What is v1, v2? 1, 0, 0. 0, 2, 0. If I take the dot product, it will be 0. Similarly, V1, V3. V1 is 1, 0, 0. V2 is 0, 2, 0. So this will also be 0. V2, V3 is equal to, so V2 is 0, 2, 0. For here, V1 is 1, 0 and 0, 0, 3. So this will be 0 only. So V2, V3 is 0, 2, 0. V3 is 0, 0, 3. So this is also 0. That means what? All three are, the dot product is 0 between any two pairs. So all three V1, V2, V3 are linearly independent. Next, you come to orthogonal subspaces. Okay, let us say there are two subspaces U, V, W that belongs to Rn are orthogonal if every vector V, small v, that means every vector of the subspace, vector subspace V is orthogonal to every vector in W. Okay, such that for every vector U, W, the V transform into W equal to 0 or W transform into V should be equal to 0. It means what? Let us say this is my space. Okay, I have, say, the subspace of this is V and another subspace is W. That I have some vectors here, small v, v1, v2, vn. Here I have some vectors, say w1, w2 and wn. Okay, so if these two spaces are orthogonal to each other, so what they mean is, for every vector you take any vector here and take the transform of that, v1 transform into w1 should be equal to 0, v1 transform w2 should be equal to 0, so on like that. All the possible combinations should be equal to 0. Then only you'll say these two are orthogonal to each other. So for example, let V spanned by V1, V2. The V subspace has two vectors V1, V2. That is 1, 0, 0, 0. V2 is 1, 1, 0, 0. And W is spanned by, say, W1 is 0, 0, 4, 5. How will you say both are orthogonal, the subspaces? These subspaces belong to what? The main space is, there are 4. So R power 4. They are the subspaces. Are they orthogonal? This is what we are checking. So how will you check? V1, W1 should be equal to 0 and V2, W1 should be equal to 0. So if you check, V1, W1 is 0. That holds. V2, W2. This is also 0. Okay. So it means both subspaces V and W are orthogonal to each other. So they are called as orthogonal subspace. Now is the important concept called as orthogonal complement. The orthogonal complement of V is orthogonal of V complement is written as like this, something like this, VT, V perpendicular. So complement, usually when I give A, you write it as A dash, right? A dash, something like this, complement of this, or A bar. So here the symbol is used like this, is equal to X that belongs to the space of real numbers and X transform into V is equal to 0 for all vectors belonging to V. So this is small v. What it means, it contains all vectors perpendicular to the subspace of V. That is the meaning. We'll take an example. So that you apply in your column space concept. So what is column space? Column space of A. So let us write it as C of A. So already understood what is the concept of column space of A. Then I can write row space of A as C of A transform. Okay. Now, what is null space? Null space I can write it as say null space of A. Then left null space. Okay. Left null space is nothing but null space of A transform. Now, what is the relation between them? You already know from rank nullity theorem. Okay. So rank is nothing but the dimension of column space of A. So plus dimension of null space of A is equal to number of columns. So if I take number of columns from a matrix, I can form the column space of A. What is the relation between column space of A and null space of A? That is the thing here. So they are saying they are orthonormal. That is null space of A is equal to C of A transform. That means row space is orthonormal complement to the null space of A is orthonormal complement to row space. Left null space, that is null space of A transform is equal to, it is orthonormal to C of A. That is the meaning. So what exactly it means? Means, see, always you know, see, if there is a null space dimension is not equal to 0, then only we'll have infinitely many solutions. That means what? Null space dimension is not 0, that is greater than say or equal to 1 only when we have some dependent columns in my matrix, right? So that means what? If there is no dependency, null space is complement, orthogonal complement means this is my xy plane, this is my xy plane, say this is my column space of A, column space of A. Okay, now my null space is orthogonal complement to this is say my null space. So the angle between this plane and this is 90 degree. That is the meaning. So they are complement, orthogonal complement to each other. For example, let us say A is equal to this column matrix. So if you calculate, I directly written here, if you calculate the rank of this will be 1. What is row space? So first you find the column space of this. Column space of A is equal to, what is that you get? So this is a dependent column, this is independent column. So column space is equal to span of this vector 1, 2, 3. This is how we find the column space. Okay. So this is the basis of column space of A. Next, what is row space of A? Row space of A is column space of A transform. So that is, if I transform this matrix, I will get it as, so I will so write this transform of this is 1, 2, 3. So this is A transform, and I have 3, 6, 9. Right. So now what is column space of this? You see the column space of this, it is nothing but these two are dependent. So I can remove this two column here. So column space is 1, 3. So this is span of 1, 3. Okay. That is nothing but your row space. Now, what is null space of A? The null space of A, you can calculate it as x equal to minus 3 comma 1 because it satisfied Ax equal to 0. So what is null space? So to calculate Ax is equal to 0. So what is A? Already they are given. So this becomes what? What is the equation you form? So A is 1, 2, 3, 3, 6, 9. Then X is, you multiply them. So first you reduce it into row echelon form and then you form the equation. So if you find out the solution like that, you will get X equal to minus 3 comma 1. Okay, minus 3 comma 1 satisfy this set of linear equations for the null space A. Now, so what is this? We check here. The null space of A is equal to, what is that you have written? Null of A is equal to C of A transform. Here both are orthonormal complement. So if we say null space of A is minus 3, 1. What is column space of A? 1, 3. So these two, if you take this, see, if I draw this, there are only two values, x, y. Let me take only x, y. X is minus 3. Minus 3 means somewhere here, and y is 1, somewhere here. This vector is, say, somewhere here. Okay. Now, what is this column of A transform? That is 1 and 3. So 1, okay, and 3. So x is 1, y is 3. You observe here, they're in the plane, okay? They're not in 1D here, 2D. So this is their orthonormal, sorry, ortho complement of each other in 90 degrees. That is the meaning. Next. So here the example is given. Now we'll go to the orthogonal matrix. Okay, let us say a matrix, square matrix Q with R n square, that is n into n cross matrix, is orthogonal if this property is satisfied. Q transform into Q is equal to, or either way, both are commutative and this should be identity. If you see this, that implies what? One is the inverse of the other. That is the meaning. So orthogonal matrix preserves length and angles. We'll see. Okay. What are the properties? So Qt is equal to Q into Q is equal to I, means Q transform is equal to Q inverse. So that is the first property. Second is the determinant of all these will be always equal to mod of 1, that is plus or minus 1. Only the direction will change. So that is called as volume preserving. See, orthogonal matrix, its transpose is inverse. Volume preserving means they will not stretch or shrink in this space. Columns and rows for an orthonormal set. These columns and rows forms an orthonormal set, that is mutually perpendicular and unit length. So if I take a matrix and then if I take the dot product of that, then I will get the each row and each column of the same matrix will be perpendicular. Then length of Q into this matrix, orthogonal matrix Q into some vector x, okay, is equal to length of this. The length of both will be same. You will see the examples. Now, product of orthogonal matrices is orthogonal always. These are the 5 standard properties. Now, first property, let us understand. If Q is orthogonal, that means Q transform equal to Q inverse. That means what? Multiplying Q transform undoes the effect of Q. So if I have Q and then I multiply it by Q transform, so whatever the effect of Q was there is not there. So I'll get an identity matrix. That is the meaning. So if you check this, these two are, this is orthogonal. This is also orthogonal. Now, determinant is plus or minus 1, meaning orthogonal matrices preserve volume. That is, I told you, determinant equal to 1, that implies rotation. Minus determinant equal to minus 1, it implies the reflection. See, the size, it will not shrink, okay, or expand in the space. It will preserve the volume. Volume in 3D, if you take, It will not shrink. Whatever volume produced by this matrix is same. Only thing is it rotates. Can rotate. Why rotation is important? To study different properties, okay, after application. And it gives the determinant of -1 means it gives the reflection of that. Okay. So let us take this example 1 by 2 minus root 3 by 2, root 3 by 2 and 1 by 2. So the determinant is 1. So interpretation 2D rotation by 60 degree because determinant is +1. If it is -1, it's the reflection. Why it is rotation by 60 degree? This is important. So how it is given? A 2D rotation by an angle theta is represented by this orthogonal matrix. Cos theta minus sin theta, cos theta. Now if you check, this is an orthogonal matrix. Okay. Because their dot product is 0. That is cos theta into minus sin theta is minus sin cos theta plus sin cos theta equal to 0. So to take the previous example, what is that they are doing? That is 1 by 2 minus root 3 by 2 plus root 3 by 2, then minus root 3 by 2 and 1 by 2. If you observe here, this is nothing but cos 60, sin 60, sin 60 and then cos 60. So this actually is rotating counterclockwise. So say that initially somewhere it was here, okay, the matrix, the vector. So counterclockwise 60 degree. Now it is here, but the length will remain same. We'll see that next. Okay. That is the property of this matrix. When you apply this matrix to vector, I'm saying this, okay, they rotate by 60 degree. 60 degree somewhere here. Counterclockwise. So this is the standard cos theta minus sin theta, cos theta. Okay, this is the 2D rotation matrix. Now columns and rows are orthonormal. Orthonormal means you already understand. So columns and rows are perpendicular and have unit length, meaning vectors point in different directions without scaling. So volume remains same. So if you check here, so if they take the dot product, it is already 0. So it is orthogonal. And the unit length. So length of this vector is 1. Length of this vector is also 1. Hence, they are orthonormal. Length preservation. So if I take a matrix, orthogonal matrix Q and multiply it by some vector X, okay, so check the length of this. This will be equal to the length of X. So how it will help? Orthogonal matrix preserve the length of vectors. Only direction may change. That is the meaning. So determinant when it becomes -1, it implies there is a change in direction. There is a reflection. That is the meaning. So let us take this x equal to 3, 4, it's a vector, and this is my orthogonal matrix. So if I multiply this, I will get this column vector 4 minus 3. We check the length of this. Length of this is 3 square plus 4 square is 5. Length of this will be q into x will be 4 square plus minus 3 square. This is also equal to 5. That is the property. Now the last one is product of orthogonal matrices also orthogonal. So if you check the product of this q1 q2, we'll get it is -1 0 0 -1 is also orthogonal. What it means? Product is reflection plus rotation. There are two things, properties that we can apply on the vectors using orthogonal matrices. That is, one is rotation, already seen the rotation matrix, and the other one is the reflection. So when I in my determinant, if I take a orthogonal matrix where determinant is equal to 1, then it implies rotation. Okay, rotation by some angle. Reflection means what? When the determinant is equal to -1. Reflection means it is just changing the direction. Okay, so reflection, for example, initially object was here. Okay, now if I rotate, say I will rotate it by some theta. So it comes somewhere here like this. So this, there is no change in the volume. Volume remains same. Okay. Now reflection means what? If it was here, say if I change some or multiply this with this and I get a determinant as -1, then this is a reflection of it. There is no change in the volume. Okay, but only reflection. If you want both, you can say it as mirror image. If I want both, then I have to multiply two orthogonal matrix to get both reflection and rotation. If you go back here, so here this is rotation. Okay, because determinant, if you check here, cos square theta minus tan square theta, minus of minus tan square theta is, that is determinant is 1. So it's only rotation. If I want reflection, then the determinant should be -1. Okay. So thank you for watching. Please like, subscribe and share. We'll continue with few more matrices and different types of projection of vectors in the next video. Thank you for